Hello everyone, welcome to the second lecture on Introduction to Multi-Agent Systems. I'm Dr. Twinkle Tripathi. In today's lecture, we'll understand a little bit more about how do we model the interactions of agents within a network. So let's get started. Just to remind you a brief recap of what we discussed in the previous lecture. So what exactly are multi-agent systems? Now, multi-agent systems, as discussed before, are composed of multiple interacting entities. Now, please remember that these interactions can be either cooperative or antagonistic in nature. And in the previous lecture, we also discussed that these entities can have different kinds of models, like a single integrator or a double integrator or a unicycle model. Now, what are some of the common tasks or applications that we use these models for? The first one would be of a synchronization kind. Now, in any synchronization application, the agents generally achieve agreement on some common state by all of the agents, meaning if there is certain, for example, if it's a wireless sensor network where the sensor nodes are trying to arrive at a temperature value of a certain region, then consensus is achieved if the temperature of all of the nodes become equal. So this becomes a synchronization task. Where else have we seen synchronization? We have seen synchronization in the flocking behavior in the V formation among birds. So if you see, if this is the final steady state behavior where all of the agents are actually moving in a V shape, then the velocity vectors, as I have marked here, are aligned in the same direction for all of these birds. Now, yet another kind of application or task that we can achieve using a multi-agent system is a coordinated task or a coordination task. In coordination kind of tasks, what we do is we say that the agents apply some sort of a collective effort which now adds up to achieve some team objective. What is an example of it? Now, to understand that, let us see these set of drones which have now distributed themselves uniformly. If you see, all these spacings are actually the same for each of the drones. Now, what they can do is they can provide or do surveillance of some particular agent which is now within or contained within this encirclement. So in such objective, each of them makes a certain effort. For example, each drone now monitors the region around it, and since each of them does it, we say that eventually the overall network achieves a certain task, which in this case is the surveillance of this drone which is within them. So we discussed a little bit about what these entities are. Now let us try to understand how do these entities actually communicate with each other or talk to each other when they are within a certain network. But before we can actually start talking about that, let us understand a little bit about how sensing or communication works in networks. So we understood now how we can model these entities. Now let us understand how these entities actually communicate with each other within a network. Now, to begin with, let us assume that we have several agents within a network. Now, and each one of them is trying to communicate with its neighbors or with any of the agents in the network by actually broadcasting its information. So what happens when all of these agents start broadcasting their information simultaneously? Then the communication channels over which they're actually talking to each other can actually get saturated. And then the transmission becomes quite poor in this channel. which can affect the overall performance of the multi-agent system. So meaning we must remember that in practical systems, there's actually limited bandwidth that we can get while we are operating, meaning the communication that we can allow for these agents distributed over the network is actually limited. So we understood how we can model the agents in a multi-agent system. Now let us try to understand how does the information exchange happen among the agents when they are distributed over a large network or over any kind of network. So several aspects come up when we try to model the information exchange in multi-agent systems. The first one pertains to the communication bandwidth of the network or the communication channel. Now, in real world systems, the communication bandwidth is generally limited. So, let us consider a network where there are several agents and each one of them is trying to broadcast its information. Now imagine all of them trying to broadcast the information simultaneously. In those cases, what happens is that the communication channel over which the agents are broadcasting the information gets saturated or can get saturated in a practical system, as mentioned here. Now, when a certain communication channel gets saturated, then obviously there's a sharp deterioration in the communication system, which leads to a poorer functioning of the overall system. And please, it's important to note that most of the practical networks actually have limited communication bandwidth, meaning when we are designing a system, we must keep this in mind, that this is one of the limitations which we always have to take into account. The second aspect is a limiting sensing capability of an agent. Now, so what can also be done is generally agents can also be given on-board sensors using which they can actually infer or sense the information of some of the agents who are near to them or their neighboring agents. What are the examples of some of the sensors that can be on board these agents? Some of them are vision sensors like cameras or range sensors like sonars, IR sensors or laser scanners. Now, let's try to understand. If a certain agent has a camera on board, then it can only sense things in its field of view, which for a camera is generally limited. So, any agent which comes into this field of view can be sensed by the first agent. So, if we number them 1 and 2, then 1 can obviously sense agent 2 only when 2 comes within the field of view or FOV as it's commonly called of agent 1. Now, most of the times real world cameras actually have limited field of views, meaning as we can see in this image, only within this sensing region or field of view it can sense agents. Now, what happens is that every sensor that is given to us most of the times comes with limited sensing capabilities, meaning that the agents, now even though there are several agents in a network, they cannot sense each and every one of them. They can only sense agents which for a camera sensor is within the field of view, or if it is any other kind of sensor, if it is within its sensing capability, only then it can sense the other agents. This actually leads to a graph theoretical modeling of the networks in multi-agent systems. Now, if there are several agents, let's number them. Now, if you see here, agent 1 can actually sense agent 2. So, let us write it. Two similarly can sense 3. And 3 can sense 4. And 4 can actually sense both 3 and 2. In these cases, how we model the network is that we say that the interactions are modeled as graphs where an edge exists between two agents only if there is a communication between them. And the edges are marked by the communication and the nodes are the agents themselves, meaning agents simply form the nodes or vertices of the graph, and an edge connecting between them simply represents a communication between them. So, we see an image here explaining the same. So, we have for every agent, the circle given like this is its sensing region. Then we can see agent 1 can actually sense 2 and 3, which can also be seen through the two edges given like this. Similarly, agent 2 in its sensing region can sense both 1 and 3, which we can see here. Similarly, for 3, agent 3 again can sense, agent 3 can sense both 1 and 2 as shown here. So, this is how we draw the graph theoretic representation of the network. So, now for any given pair of nodes, is the communication always bidirectional in nature? What does that depend on? Now, to understand that, let us consider a group of robots which have onboard cameras. Now, obviously, the cameras on the robots need not face each other simultaneously, meaning let us say this is agent 1 and this is agent 2. There is a possibility that agent 1 can see agent 2, but 2 cannot see agent 1. In this case, the edge marking the communication has to be bidirectional, has to be directional in nature. It is bidirectional only if the camera system looks like this. Now, 1 can see 2, 2 can also see 1. In this case, we will simply have a bidirectional edge, or simply we need not mark any direction, meaning the communication is bidirectional. And in the previous case, so what we haven't talked about till now is what should be the direction of the arrow which makes the edge directional. So, let us look at that. So, we understood that the edges can actually be directed or undirected. Now, let us see how do we figure out the direction of the edge. Now, suppose we have some two agents I and j, and this is the arrow direction. Such a direction means that agent I is actually sensing, agent j is sensing agent I, right. So, please know that this is only a notational thing. There are several references in the literature which actually consider the reverse direction, meaning if it is this way, they say that j gives information to I. So, this is also possible. This is another way of representing the graph, and both of them are correct, but in this, throughout this course, we will follow this format, where j receives information from I. But as I mentioned, this is only a notation and can be reversed if one is interested. Now, for any given, suppose we have drawn a graph. Now, the question is, let us again take the example of robots. At time t equals 0, suppose there are several agents. We just consider 2 of them now. Now, we know that 1 and 2 can sense each other. Let us say as time evolves, 1 now takes a certain path and now points this way, and 2 similarly takes a certain path and points this way. So, let us call this some t equals t bar. Now, you see, over time the network can actually change. Initially, this was bidirectional, but now only 2 can sense agent 1. Based on that, we actually divide the kind of networks into 3 types. The first one is a static network. In a static network, the graph does not vary with time, or another way of saying is that yes, the edge set doesn't vary with time. An example of a static network could be a wireless sensor network, where the sensor nodes are actually static, and we assume that the communication strength does not go bad or deteriorate too much over time, meaning the sensor node has a certain graph structure for at least for a large amount of time, making the network static in nature. Another kind of a network is a dynamic network, where the graph or the edge set is actually time varying. An example of it is the mobile robot case, which we just discussed. A mobile robot with limited sensing capabilities, where if a certain robot turns, then there's a very high chance its set of neighbors can actually change with time, meaning its the set of edges that it has in the graph can actually change with time. Now, there's yet another kind of network, which is known as a random network. Now, what happens in a random network is that the existence of an edge is actually given by a probability distribution function. An example of it is a communication channel, a communication network, where the communication happens based on a certain probability distribution function. Okay, having understood how we model the entities, and then having understood how these entities or agents actually communicate with each other, now let us try to put together all of this information into one real world example, or a motivating example which helps us understand multi-agent systems a bit better. So, let us start. We will talk about the French-Harari de Groot model, which models the interactions of agents in a social network. So, what we see here are a group of people who are all talking to each other. So, let us start with a group of some n individuals, where each individual actually has a certain estimate of some parameter or topic, or they have a certain opinion on some topic. And what each of them is doing is, they are talking to each other about the same topic and trying to update their own opinions in the process. So, let us put together some more notations here, or let us define some more variables here. We call Pi as the estimate of a certain parameter that individual I has, or in simpler words, the opinion of individual I on a certain topic. Now, as we discussed, agent I actually updates its information based on the interaction it has within the network. So let us try to understand a bit more about these interactions. Now what every agent does is, it places a certain trust index on each of its neighbors or whoever the agent knows and is talking to. Let us say we have a large network here. And the agents are actually scattered all over the network. In general, in a real world network, obviously every one of them doesn't know each other directly. So we'll assume that maybe this agent knows only some of the agents, and it talks only to these set of agents in order to update its opinion. But remember that it does not necessarily place equal amount of trust in each one of them, meaning it now introduces a term Aij, a coefficient or a weightage, a weighting factor maybe, that it uses to update the information. So there are certain ways in which we define Aij. So first of all, every Aij means it is how much, or it is the trust index of agent I for agent j or individual j. And every Aij is greater than equal to 0, and the sum of all of the Aij's, as j varies from 1 to m, is actually 1. Now what is m? M is simply the number of people that agent I knows. For example, in the figure that we just drew here, let's number the agents. So m for agent 1 is actually equal to 5. So we can write it actually mi, meaning the number of people that agent I knows is actually a function. It can actually vary depending on what I is. So here m1 is actually 5. So what does the French-Harary-de Groot model look like? So this is the update rule. Now, at the next instant of time, the updated parameter estimate or opinion of individual I is simply a summation of this, which is a weighted average of all of the opinions of the neighbors it has. For example, for the previous figure which we drew, we will write it in this form. P1 plus is equal to up to, I think, A6. I'll quickly check. Now notice that while the agent obviously talks to other agents, we still add a term A11, which is simply the self-weight or the self-importance which the agent has, meaning it also values its own previous estimate as well. So this is, we can call it a self-importance term maybe. Okay, so we write down this model for every agent in the network, meaning we have some expression for P1 plus, we have some expression for P2 plus, and we keep on writing it for Pn plus. What we will get here, if now we try to write it in the form of a matrix. Up to Pn. So note that this is simply the model pertaining to all of the agents in the network. So meaning, we call this the adjacency matrix generally, but we'll talk about it in more details eventually later in the course. But let's call this A and this as the vector P. then we can write P plus is equal to A into P is what the model becomes. So now let's write it for a certain number of time steps. Let us say these are my time instants, and at P equals 1, P of 1 at the first instant, this is what my opinion vector is, or the estimate is. At the next instant of time, P of 2 becomes A into P of 1, and I can substitute the value of P of 1 from here and write it as A into this. It becomes equal to A square P of 1. Similarly, P of 3 becomes A cube, P of 0. This is P of 0, and similarly P3 becomes A cube P of 0, and similarly I can write the expression for the opinion at the kth instant of time. It becomes equal to A to the power k P of 0. So this is my final, or the opinion at the kth instant. Now this is exactly what's written here. We have all of the states at given instant of time, and these are the initial value of the states. Some natural questions now arise. First of all, so we know that all of the agents are interacting within the network, not necessarily to each one of them, but within the certain groups. They're all talking to each other. So will the agents finally agree on a certain topic? Will they have the same opinion about the topic? We do not know that. We cannot be sure. So what are the conditions when we can ensure that all of these agents actually agree with each other? Does it have to do something with the initial conditions of the agents, or does it have to do something with the network topology, or does it have to do something with the update rule itself? So how do we analyze these kind of mathematical models? Now, in order to analyze these models, so this can be summarized and written this way. We have the opinion vector at kth instant of time is equal to sum A to the power k P of 0. Whether P of k converges or not depends on the properties of A to the power k heavily. So how do we go about analyzing this? In order to analyze mathematical systems or behaviors of this system, we will need to employ tools from linear algebra, first of all, also matrix theory, and also graph theory. So before we can actually answer this question about do we get a consensus among all the agents or not, we will first need to know a little bit of preliminary material from each of these topics, which is something that we will cover in the next lectures to come, so that we can finally go about answering this question, do we actually get a consensus? These are the textbooks that we will follow to understand some of the material. The basic material of graph theory pertaining to graph theory and multi-agent systems are based primarily on these two reference books, and the linear algebra material is covered from the book Linear Algebra Done Right by Sheldon Axler, and the matrix theoretic part of it is covered from Matrix Analysis by Horn and Johnson, the book by them. These are the references for the some of the images that we used for the lecture and other basic material. Thank you.